Hi, hello friends. Welcome to T Academy. Today I am going to discuss the previous AE electrical paper questions. As a part of this series, I had early covered networks, control systems, and power electronics. Now, in this video, we'll discuss about the power system questions here. Okay, so without wasting your time, we'll start the question here. If you have any questions or queries about my YouTube channel and other doubts, you can contact me freely to my mail ID, that is teea4u@gmail.com here. Okay, so some of you are asking me about the solves or previous sub-engineer papers and as well as some JLM papers, right? So you can send me the question papers to this mail ID and I will try to solve the question papers for you, right? So note on this mail ID and you can contact me to this mail ID here. Let's start the question of a power system here. If the real power demand is suddenly increased, frequency of the system will. The options are increase, remain same, decrease, and first increase, then decrease. The answer for this question we'll discuss here. The first way of explanation is we know the accelerating equation. If you have studied about the accelerating power, so Pa is equal to, it is nothing but the P mechanical power, okay, M is mechanical minus P electrical power here. Now the real power demand increases means the electrical power demand increases. What about the accelerating power? Accelerating power decreases. Once the accelerating power decreases, automatically the speed is going to be decreases. As the speed is decreases, we know that formula Ns is equal to 120 F by P. So automatically frequency will decrease here. So the frequency of the system will decrease. So the other way of explanation this is, that is the kinetic energy stored in the rotor of the alternator is proportional to frequency square. As a real power demand, yes, you know, the real power demand increases, then the kinetic energy is going to be decreases, so that frequency is going to be decreases. So both the way the answer is, it is going to decrease the frequency. So let's move to the next question here. Yeah, this is a somewhat standard question. So this question also a previous gate examination question here. The question here it is, two generators rated at 200 megawatts and 400 megawatts are operating in parallel. Their governor droop characteristics are respectively 4% and 5% from no load to full load. At no load, the system frequency is 50 Hz. When the supplying a load of 600 megawatts, the system frequency is. So this is a previous year gate question. Okay, you can find that gate question in the gate examination papers. Now I am going to discuss a solution for this gate examination. So already I discussed this question in my previous AE papers. Now what is the solution for this? Let us assume there are two generators, name it as a P1 and there is another one is a P2 here. Now so P1 by let's 200 megawatts is equal to, let's x value here, x by, okay, how much percentage it is drooping? 4. Okay, now from this x into 50 is equal to, so P1, let it the equation number 1 here. And similarly for the generator 2, so P2, it is going to deliver how much? It is going to deliver 400 megawatts is equal to x value divided by how much drooping it is, 5% here. That implies, okay, so from this 5 8 ja 40, 80 here. Okay, so x into A2 is equal to, so P2, let it the equation number 2 here. And as per the question, there are two generators supplying a total load of 600 watts. So P1 plus P2 is equal to 600 megawatts. So equation number 3 here. So by taking these three equations, and there are three unknown parameters, so we can find the value of x here. So how can you find the value of x? Substitute the value of P1, P2 here. That is x into 50 plus x into 80 is equal to 600. So from this x value you can get it as 4.615. So 4.615. Remember here it is in percentage here, okay? 4.615. Now how much change in frequency? So change in frequency is change in frequency. FC we can call as FC is nothing but it is actual frequency is how much? Supply frequency is Fs minus, okay, so Fs into x percentage here. That implies 50 minus 50 into 4.615 divided by 100 here. Okay, so once you are getting solved this, you will get the answer as 47.69. 47.69 hertz. So approximately we can write it as 47.7 hertz here. So for this question the answer will be 47.7 hertz here. So answer is D will be the right answer. That means what's the meaning of this one is, if there are two parallel operating generators individually having a 4% and 5% drooping characteristics, when they are combining together they will have a drooping characteristics of 4.615. Because of this one there is a change in frequency. How much frequency we have here? 47.7 hertz. So this is the change in frequency here. Let's move to the next question here. Right, so this is a theory based question here. In this question, the capacitor connected in series with the line is used to enhance power factor, enhance power system capability, decrease the losses, decrease the power transfer here. Now what we are doing it is, there is a transmission line here like this, which having a inductance and resistance like this. What we are doing here it is, a capacitor is connected in series with the system here like this. Now what it is the impact it is going to make here? Generally the formula for the power system is P is equal to EV by X into sin delta. Okay, now let us say XL here. Okay, now when we are adding this capacitive reactance Xc here, now the power system formula change here it is EV by XL minus Xc value. Okay, it's a Xc and here it is a XL and here it is a R. Now as of when we are inserting this capacitance, automatically this part is going to be decreases, so that power will increase. We can call as a power system stability. Okay, so it is going to improve the power system capability. Okay, so it enhances the power system capability. So answer is a B here. Okay, so B. We'll move to the next question here. Right, so this question is from the power system protection. The question is about a loss of excitation protection. Loss of excitation protection E scheme for a large generating unit employs. It is going to employ offset Moe relay. So it's one of the standard bit here. Offset Moe relay is used for the loss of excitation. Next question here. There are some theory questions asked in the power system here. Next one is equal area criteria is a method to determine. So equal area criteria is a method to determine the transient stability. Okay, it's used for the transient stability. So equal area criteria is used for the transient stability analysis or studies. If the accelerating area is equal to the deaccelerating area, then the system is going to be stable here. So you have seen this type of diagram here. Okay, so here we have some accelerating area and here we have some deaccelerating area like this. Okay, so when the A1 and A2 are going to be equal, then we can call as the system is going to be stable. So that all this things are discussed in the steady state stability analysis. Okay, so equilibrium criteria is used for the transient stability analysis here. Okay, so I am not going to discuss the in-depth detail. Why? Because if we start the discussing about the in-depth, it will take more than 2-3 hours to discuss each and every question here. Now next question here, in the rotor angle of stability, the condition for stability is, in the rotor angle of stability, the condition of stability is nothing but d delta by dt is equal to 0. So we can call this one as a power angle here. So power angle is nothing but d delta by dt equal to 0 here. Okay. Next question. A transmission line is operating with a phase shift of 80 degrees between the two ends. If the load is suddenly increased here, so let's say Vs here, and there is some resistance inductance line is like this, and here we have Vr. Okay, if you have transmission line XL here, so general formula is P is equal to EV by XL into sine delta, or we can call it as a Vs Vr by XL into sine delta here. Now what is happening is, the angle between the supply voltage and the receiving end voltage is already having 80 degrees here. Okay, now suddenly the load is increased here. So when the load is increased, to cope up with the load, the delta value has to be increased. That means the phase displacement will increase here. So answer is A for this question here. Next question. So it is a formula based question here. If the regulator R is equal to 1% and a damping coefficient D is equal to 0.8, the change in generation of area of drop in the frequency of 0.015 per unit in PU is, okay, the change in generation contributed by the load is delta Pg is equal to, I'll write it down here, delta Pg is equal to minus change in frequency divided by the R here. Okay, so now the drop in frequency is how much? It is minus 0.0015, okay, divided by the R value is 1%, means write as a 1 by 100. So once we solve this, we will get the answer as a 0.15 per unit here. So answer will be C here. Okay, we'll move to the next question. Next. So this question is from the transmission line faults. In LLG fault, the relationship between the sequence voltages is that we have a three sequence voltages: positive sequence voltage, negative sequence voltage, and zero sequence voltages. In case of a double LG fault, the relationship between the sequence voltages is the positive sequence is equal to negative sequence is equal to zero sequence voltages. Suppose in case in which sequence the currents are same, means in case of LG fault, okay, so that is a positive sequence current is equal to negative sequence current is equal to zero sequence current. All the currents are in series. Okay, suppose if there are equal voltages, means double LG fault. In case of only currents are same, means it is going to be LG fault here. Okay, and the next question of this video: a larger power system is represented by Thevenin's equivalent. The ETH and ZTH are 0.9 per unit and 0.25 at angle 90 per unit respectively. If a shunt capacitor bank is connected to raise the voltage, to raise the bus voltage to 1.0 per unit, the MVR rating of the capacitor bank is. Now assuming that here in the given question itself, they assume that the base MVA is 100 and the base kVA is 138. Now here what we need to find here. So here we need to find the MVA rating of the capacitor bank in order to make the voltage from the 0.9 to 1.0 here. So I'll write down the formula here. The change in voltage delta V is equal to, that is the QSH shunt capacitor reactive power divided by V into XL here. Okay, what is the delta V? Delta V is nothing but it is a voltage riser from 0.9 to 1.0. That means we can call it as a delta V is nothing but 0.1. Difference between the 0.9 and 1.0 is 0.1, which is equal to, okay, so here we need to find the value of QSH divided by, it is raising the voltage to 1.0 into XL is what, into 0.25 here. Yes, right. From this QSH, what you can write, QSH is equal to so simply 0.1 divided by 0.25 here, so which is nothing but 0.4 per unit, so which is nothing but 0.4 per unit here. So we want to convert this value into actual value. Okay, so what is the formula? So anything Q per unit is equal to Q actual value by Q base value, right? So Q per unit, you know what is that, 0.4, which is equal to Q base Q actual value divided by base value is 100 MVA. So from this, Q actual value is equal to 0.4 into 100 MVA is nothing but 40 MVA is the answer here. So answer will be D here. So that's it, friends. For this session, we will continue the next subject in the next upcoming video. Thank you, friends. Have a nice day.